Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everybody. My name is Frank Seide. I'm standing in for Kenneth Tran. I'm working in the speech and dialogue group here, but in the past half year, I sort of slid into this role of being sort of the architect for CNTK. And because of that, I'm super excited to welcome the speaker, Song Han, Chinese Han Song.
Yes.
Is that right? Okay.
Yeah.
He is a fourth year, I'll read this, there's a lot of information on here. So he is a fourth year PhD student with Professor Bill Daly at Stanford University. His research interest is deep learning and computer architecture, like I think many of us have the same interest here right now. Currently, his research is improving the accuracy and efficiency of neural networks on mobile and embedded systems. And I think that's a very important topic that I'm particularly very interested in. He worked on deep compression that can compress state-of-the-art CNNs by 10 to 49 times. So the work was also featured in the Next Platform, Tech Emergence, Embedded Vision, and O'Reilly. And this is actually how I learned about the work. And this work actually has won the Best Paper Award at ICLR in 2016. So let us welcome Han Song.
Yeah, thanks for the introduction, and I'm very glad to be here to give a presentation at Microsoft. So today I'm going to talk about deep compression, DSD, and EIE, which is Inference Engine. So a brief introduction of myself. Currently, I'm a fourth-year PhD at Stanford with Professor Bill Daly. So my research interest is in model compression and hardware acceleration. And my advisor is Bill Daly. He's the professor at Stanford and also the chief scientist at NVIDIA. So this talk consists of 4 parts. The first part, I will talk about deep compression. So how do we compress deep neural networks, make it 10 times or 50 times smaller, but have the same accuracy? The second part, I will talk about DSD training, which stands for Dense-Sparse-Dense training, which is a regularization method that, given the same model size, same model architecture, to improve the accuracy across speech recognition, image recognition, and image captions. So the third part, I will talk about SqueezeNet plus. So it will be a design space exploration to talk about how do we tune the hyperparameters in deep neural networks. And finally, I will talk about hardware project, which is an ASIC called EIE accelerator, the energy-efficient inference engine that works on the compressed model that accelerates the DNA model by 13 times compared with GPU and 3,000 times more energy efficient than GPU. So let's start. So deep learning is the next wave of AIs powering image recognition, speech recognition, natural language processing. So it is very accurate, but given those embedded systems, for example, phones, drones, robots, glasses, and self-driving cars, the computation is usually very intensive. And where to do the compute, on the data center or on the mobile system? So there is a collision of ideal with reality. So mobile system, we have limited computation power, but deep neural networks requires billions of multiply and adds. And also, mobile systems have limited memory and storage, but deep learning models are pretty huge usually. And also, mobile systems have limited battery and power, but running deep neural networks is really power hungry on the GPUs. So one of the critical issues that brings those problems is the model size. For example, from the software perspective, app developers suffer from the model size because once the app is over, say, 100 megabytes, Apple Store does not allow you to download until you connect to the Wi-Fi. Not only software engineer, but also hardware engineer suffers because if we see this chart, we ask the question, where does the battery consume all the energy? And the answer is DRAM access. So one DRAM access is equal to more than 100 multiplications and adds. So you do one DRAM access, you can do 100 multiplication and adds. So one critical issue is really to bring down the model size, so to reduce the memory footprint of running deep neural networks. Put them all in cache, all in SRAM, no need to go to DRAM. So I propose 3 solutions. The first one, the problem is model size. The solution is deep compression to make it smaller, but have the same accuracy, no sacrifice of accuracy, and then have speed up. And the second thing is DSD training, dense-sparse-dense training. So given the same model size, how do we make it more accurate? Given the same size, make it more accurate. And it's a general method applying to vision, speech, and natural language processing. And the third solution is the EIE accelerator, which is a hardware ASIC that targets, solves the latency, power, and energy consumption problem. So let's start with deep compression. Give it an overview. Deep compression can compress AlexNet by 35 times, make it around 7 megabytes without hurting accuracy, and VGGNet by 49 times to only around 11 megabytes, and GoogleNet to only 2.8 megabytes. And even the really efficient SqueezeNet, which is proposed recently, but also by 10 times, making only 470 kilobytes. And recently, our SqueezeNet version 1.1 has even better accuracy than AlexNet. So they all have no loss of accuracy of ImageNet compared with the baseline model. So after compression, the weights can fully fit on SRAM cache, so no need to go to off-chip DRAM, which brings a complete new space for hardware design. So how is deep compression done? So there are 3 stages. The first one is network pruning, get less number of weights. The second step is weight sharing. So for per weight, we have less number of bits to represent each weight. And third one is Huffman coding, which is a lossless compression method. I will start with network pruning. So this work was done in the NIPS 2015. So pruning a network is pretty much like pruning a tree. So you get rid of those redundant connections and only keep those useful connections. So this has been explored for more than 20 years. So it was first proposed in the 1990s by Yang Kong, and we basically removed the data from the table and applied it to modern neural networks and found it worked extremely well. So we pruned the synapses and pruned the neurons as well. So after pruning, only those useful connections are left. So how do we decide the criteria for usefulness? So the criteria I used is just based on the absolute value. If the absolute value is small, get rid of it. And this year I saw a lot of NIP submissions talking about the new heuristics about pruning. So hopefully we can see more. So what is the motivation? So the motivation comes from our human brain, how we are evolved. So at birth, this is a result by published in Nature. At birth, a human have roughly 50 trillion connections in the brain. And at 1 year old, it suddenly surged to 1,000 trillion. It peaked. And then at 10 year old, and then as we grew up as adult, it only get waned and get down to 500 trillion connections. So it first go up and then pruning and go down. So does the same pruning mechanism work on the artificial neural network? And the answer is yes. So this is the AlexNet, and this is VGGNet. The green part shows for each layer how much can we safely prune without hurting the accuracy. For example, for conv layers, usually we can prune away roughly 2/3 of the connections without hurting the accuracy. But the first layer, which interacts directly with the image, is very sensitive and cannot prune too much, and it has only 3 channels. And FC layers, usually you can safely prune away 10 times. So both conv and FC layers can be pruned. So a conv layer is already sharing the kernel in different places. That's why it can prune less, and FC layers can be pruned more. Since FC layers dominates the total number of weights, the total number of connections we can prune away is roughly equal to the number of connections we can prune away for FC layers. So this is a figure illustrating how much can we prune and how much accuracy will we sacrifice according to different pruning methods. So I examined with 5 different methods. There are 5 lines here. We can see that the dashed line is without fine-tuning. So we just prune the parameters, and then we don't retrain the network. And we can see we can get pretty much 50% free lunch without retraining, just 1 minute or a few seconds prune away the parameters, we can get a free lunch of 50%, getting rid of 50% of the parameters. And then with proper retraining, however, without retraining, when we prune away more parameters, the accuracy begins to drop with either L1 or L2 regularization. So it's interesting to see that with proper fine-tuning, sometimes the accuracy can even increase here. And this brings our later work on DSD training. We'll talk about it later. But the really big gun, the most powerful method is actually to do the pruning, retraining, iteratively. So don't prune that much in one iteration, but you do that iteratively to prune away 90% of the parameters. And we can see there is no loss of accuracy here.
Do you always train with L2 from the beginning in this case?
Yes, this is trained with L2 regularization. And this is L2, this is L1. Without pruning, we can see L1 works better. But with retraining, L2 actually works better.
Did you tune the L2 hyperparameter for this?
L2
The strength of the L2, how did you tune it?
Oh, so for the regularization, I didn't tune it. Just use the original learning schedule, training schedule. I didn't tune the weight decays.
And not the weight decay, the actual strength of the L2.
The strength of the L2, yes. I used the same regularization strength as the original dense training phase. I didn't change that part. Oh. So this is the result on 4 networks, LeNet, AlexNet, and BGGNet. And we can see that we can prune away, the number of parameters we can prune away is roughly ranging from 9 times to 13 times. And the accuracy doesn't hurt. So we have seen that pruning works pretty well on CNNs and image classifications. How about RNNs and LSTMs?
Pruning, like the iteration that you made, what is the overhead of training? How many iterations do you need to go to get the same kind of accuracy?
Yeah, so I used roughly 3 iterations to do one pruning to 90%. So how about on RNNs and LSTMs? Oh, question?
So the compression rate is higher. How about the speed? Is it slower at test time?
The speed, we have a slide about speed later. I'll show you later. So pruning RNN and LSTMs. This is the work we have done pruning the neural talk, which is the image caption system. We prune away 90% of the parameters without hurting the blue score. And we can see some visualizations. For example, originally, given this image, the caption says a basketball player in white uniform is playing with the ball. Pruning away 90% of the parameters, a basketball player in a white uniform is playing with a basketball. If we prune away too much, say 95%, it says a man in a red shirt and black and white black shirt is running through a field. It's kind of getting drunk. And I believe if we are prune away 90%, 95% in our brain, I cannot stand here to talk. So one student from Stanford did a class project pruning the machine translation network. So this is the result. This is the network, the sequence-to-sequence model she worked on. And she found that pruning away 90% of the parameters didn't hurt the blue score, but increased the blue score a little bit. And this is the sparsity pattern she got of the word embedding and the LSTM different gates. We can see that for word embedding, so the dark represents that is 0. And if it's white, it means that it's non-zero. The non-zero, the most common word have a lot of non-zero, but the least common word can be pruned a lot. And for LSTMs, actually, we found for the different IFOG, the 4 different gates, the sparsity is different. The forget gate, most of them is 0. So it really means in this network, the forget gate really seldom take effect in this case. But the input gate has a lot of white dots, meaning that it makes sense because you always want to take the input. So this figure shows the weight distribution before pruning and after pruning. So we can see, since the heuristic is based on the absolute value, So lots of the weights that's close to 0 has been removed. That's why there is a big dent here and roughly forms a bimodal distribution. So this is very interesting that there are some recent work on binarizing the neural networks, right? So we can see from this picture, rather than a whole distribution like this, it roughly gives you positive and negative clusters, right? So normal, very intuitive thinking is to say, if we can further do the clustering and make it more fine-grained, so that brings the second step, which is weight sharing, to reduce the storage of each remaining weight. So that is done by quantization. So using less bits to represent each weight. This is done by first to k-mean clustering on the weights, and then generate a code book, and then quantize the weights with the code book, and then retrain the code book, and do this one iteratively. Yeah. So this is how a trained quantization works. So it differs from previous quantization that this is nonlinear quantization. For example, this is a 4x4 matrix representing the weight between the hidden layer with 4 neurons and another 4 neurons. Previously, each weight is represented with a 32-bit floating point number. And now we cluster the weights by their value. Say if one weight is 2.09, the other is 2.12, then they are both 2, and they share the same color here. So with this code book, instead of storing the 32-bit floating point, we just need to store the index. In this case, there are 4 entries in the code book. So there are can be represented with only 2-bit unsigned integer. And how about doing training? How do we train such weight shared network? A lot of them are tied together. So it's pretty simple. So we get the gradient of all the weights as usual, returned by Cafe. And then we group them by their color, by their assignment, by their group. And then we do a reduce to reduce all the gradient of the same color to a single value, and multiply this reduced value by learning rate and subtract it from the previous code book and get a new fine-tuned centroid. So we are fine-tuning the centroids, not fine-tuning the weight, the assignment. They still belong to the same group, but their centroid value can change. That's why it's called trained quantization. So previously we have seen the bimodal distribution, and now after quantization, all the weights only pick from these 16 values. There are 16 dots. Compared with the linear quantization, which is roughly from the min to the max, which representing this cross, green cross, trained quantization can really do nonlinear quantization, which gives denser centroids here when there are a lot of such parameters and really sparse around the places where there are not that much weights. So one thing I motivated from Frank's work about 1-bit gradient descent is, so currently I'm just retraining the centroid, making the centroid able to move, but I didn't allow them to change their group. They always have the same group. So maybe we can have a 1-bit stochastic gradient descent, making each weight can either jump to the left or jump to the right. So change their assignment as well. So this illustrates the weight distribution about the original network after pruning and after quantization. So for conv layer, we can represent them with six bits. So that's 2 to the 6, which is 64 discrete bars here. And how much bit per weight do we really need? And we examined both the FC layers and conv layers separately. For FC layers, we can pretty much, until 4 bits, there will be pretty much no loss of accuracy. And all the way to 2 bits, does the accuracy really begin to fall down the cliff? And for the conv layer, pretty much around 6 bits, there are roughly no loss of accuracy. And around 4 bits, the accuracy begins to drop really sharply. So roughly 2 bits and 4 bits for FC layers and conv layers.
I'm sorry, which model is this?
So this is AlexNet. Yeah, but we found that the rule pretty much generalized to GoogleNet, VGGNet, SqueezeNet, ResNet. Yeah. So this is the exact number, how much accuracy do we lose by this quantization. With 8 bits and 5 bits, there's no loss of accuracy. 8 bits and 4 bits for COM and FC, there will be roughly no loss of accuracy. And with 4 bits and 2 bits, there are 2% loss of accuracy, depending on how much do you want to save on your hardware. There is some trade-off on the accuracy. Yeah, and this figure is comparing. So both pruning and quantization are reducing the size of the parameter. How is it if we do them individually compared with do them together? We found that doing them together works really well. And compared with the cheap SVD method, it can reduce the number of parameters more, roughly 3.5% without hurting the accuracy. And one interesting question is to ask is, so we first did pruning, and then we did quantization. Can these be changed? Can we first do quantization and then do pruning? So the answer is no. So why is that the case? Because pruning first reduced the number of connections and roughly gave you the bimodal distribution like this. That already separates the weights into positive and negative part. That's a very coarse-grained quantization. And then you do such fine-grained quantization. That's the first thing. The second thing is that pruning already gave you roughly 3 times to 10 times less number of parameters. So the k-mean clustering only works on a small number of weights to do the scalar quantization instead of lots of weights. That's why first do pruning and then do quantization.
When you compare with SVD, do you also quantize SVD results?
The SVD result isn't quantized. That's just by changing the number of the values you keep.
Typically also combine with quantization.
Yeah, you can definitely do that. You can
So
definitely
if
do
you
that.
compare with quantization plus SVD, what's the gain you get?
So if you combine with quantization method, you can imagine you can make it smaller by converting from 32 to 8 bits. That's 4 times saving, right? And here at 20%, you already have like 1% loss of accuracy. Divided by 4, that will be here, but you have already 1% loss of accuracy. Yeah, let's move on. So the third step is to do Huffman coding. This is pretty standard lossless compression. So encode the weights and the index. So for those more frequently appearing weights, use less number of bits to represent. And for these less frequent appearing weights, we can afford to use more number of bits to represent. But this requires coding and decoding overhead. So this step, I didn't use this in my hardware accelerator. So this is the overall summary of deep compression. How can it compress different networks? So I pretty much examined the AlexNet, VGGNet, SqueezeNet, GoogleNet, and the compression ratio ranges from 10 times to 49 times. For GoogleNet and SqueezeNet, they are pretty much all conv layers with very little FC layers. That's why it can be compressed less, but it can still be compressed by an order of magnitude without hurting the accuracy. So now the good thing is that all the weights can pretty much fit in the SRAM cache. For example, 470 kilobytes, 2.8 megabytes. So L3 cache for a CPU is roughly 16 megabytes. So all the weights, you can fetch them from SRAM instead of go to the off-chip DRAM. So what happens when it fits in the SRAM cache? So the first thing is speed up. Just now, one question is what speed up. So we now only examine the FC layers here because that is easier to implement by just calling on GPUs. We can call cuBLAS, cuSparse. So this is the original speed on CPU, GPU, and mobile GPU, which is TK1. And the GPU is TitanX, CPU is Core i7. And this is the speed up if we use the pruned method, because all the weights after pruning, they can fit on the cache. That's why even the sparsity is less than, say, 1%, right? When you are going beyond the threshold where everything can fit in the SRAM, everything begins to change. You get less latency.
But don't you lose all the efficiency by going from dense matrix multiplies to sparse matrix multiplies? So.
Yeah, that's true. That's true. But the good thing, there are two issues. One is you lose the good thing, but you represent it with the CSC format, which GPU is pretty well optimized with their CSC or CSR format.
Okay.
Yeah, it's not the normal way. And then since the weights are smaller, they pretty much fit on the SRAM cache. That's why it gets faster and less and contains less energy. So smaller deep neural network means there will be less communication if you do distributed training, right? If you have a model server and you have coordinate multiple different copies, there will be less communication with distributed training, and easier to download from an app store, and also takes less bandwidth to update an autonomous driving car. And similarly, it's easier to deploy on embedded hardware with limited memory.
I understand your first point, because you're still training conventionally all the way up till the end, then you do the compression, right?
Oh, yes, that is true. So that basically means the original model, if you make it smaller, it can help with the training. For example, the SqueezeNet, which even before compression is 4.8 megabytes. Yeah.
Do you think there's any opportunity to apply this during training?
Apply this during training for accuracy perspective. That's what I'm going to talk next. But for memory perspective, no solution on my side yet. So this is the compressed SqueezeNet, which I uploaded to GitHub. Feel free to check it out. So this is the version that used only 8 bits, but actually it can use 6 bits. That's why this is 470 kilobytes, but the model I uploaded is roughly 660 kilobytes. So it's really hard to encode them with 6 bits in a normal computer, but you can do this. So that's the second part of the question.
When you do the quantization, you have to look up each index into your real centroid, right?
Yes.
Doesn't that make your system much slower?
With the specialized hardware, that's why we build an efficient Inference Engine, which is specialized hardware that put that special logic, the decoding logic, which look up as a register file with only 16 entries, which is pretty small. I'll talk about in the last stage of my talk.
Performance numbers that you had in the earlier slides.
That is only sparse, only uses sparsity, no weight sharing.
Oh, no quantization.
No quantization in the speed information just now. Yeah.
Would it make sense to maintain your network to be sparse during the training? I guess that's what.
Yes, that's what this one will be about. So DSD stands for Dense-Sparse-Dense training. Question.
On the previous one. So, for example, if we use SVD approach, everything is still dense. So you can still have the efficient CMD implementation. If you compare with that, in the speed-wise, you'll see which one is better. When you convert to the sparse representation, you have a lot of overhead.
So my final goal is not to use conventional hardware to do this. So conventional hardware is not good at sparse representation. Does not mean it's not correct for us to build specialized hardware for that. So every time for software designers should not be constrained by what kind of hardware we have. And later I will introduce the EIE Inference Engine that go beyond this constraint that really let you to reach the computation limit that you can have instead of limited by the hardware you have.
Could you, for this slide, say what CPU implementation you use? Was that MKL?
Yes, the CPU version library we used is MKL. So here are some, so this is the next chapter about dense-sparse-dense training, which is regularized DNNs with dense-sparse-dense training. So interesting figures first. This is showing how dense-sparse-dense training can help with auto caption. The baseline model is the neural talk, and the sparse is just sparse. DSD is trained with dense-sparse-dense training. Originally, the baseline says a boy is swimming in a pool. Sparse one says a small black dog is jumping into a pool. And the DSD training says a black and white dog is swimming in a pool. It's more kind of accurate compared with the previous things. Similarly, for this one, baseline says a group of people are standing in front of a building. And the sparse one says a group of people are standing in front of a building. Same thing, pretty much. DSD said a group of people are walking in the park. So it captured, okay, this is a park. So this is the very recent work I submitted to NIPS. Haven't too much time to have all the examples, but there are, in our appendix, there are a lot of pictures like this. So the motivation is that, so previously we saw the model size. Now we shift gear and see the accuracy, how to make the model more accurate. Okay. So one critical issue is to combat between the overfitting and the underfitting, right? So if you have too many parameters, you're likely to get overfitting with limited training data set. And underfitting, if you have too few parameters, this is hard to balance. So I used the sparse regularization to cope with overfitting, to prevent overfitting. And then after training tightly constrained network with tightly sparse, didn't work just now. After training a tightly constrained network, I free them up, get rid of the sparsity constraint, and increase the number of parameters we have. So we increase the model capacity to prevent underfitting. So the phase will be like this. This is the previous, just train a sparse network, regularize the network with sparsity constraint. We have less model capacity, but can have the same accuracy. So after the tightly constrained network, we free up the constraint, and then redense the model. You see, like those dead connections get back again to recover it again. So now we have a larger model capacity and achieve the higher accuracy. We examined with both the image classification and speech recognition and image caption. So let's see the weight distribution through the process. This is the dense original network distribution. And after pruning without retraining, those weights with small absolute value are removed. And next, after retraining, this gets softer because they get a chance to adjust themselves through SGD. And then we recover those zero weights. That's why there is a large spike here. All the removed weights are recovered. And then finally, we retrain the whole dense network again. That's why this really sharp distribution gets more flat. So these are the networks we examined to see if DSD training applies to all of them. Although we cannot theoretically prove why this works, but we did a lot of experiment, including the Baidu USA. They help us with the experiment on their deep speech network, and recently, just these days, on Deep Speech 2, which is a newer version of deep speech. So we examined with both vision networks, AlexNet, VGGNet, GoogleNet, ResNet 50, and recently ResNet 152, we did the experiment as well, SqueezeNet, and deep speech and neural talk. And we found actually it worked on all these networks. For example, on AlexNet, through baseline and sparse and dense-sparse-dense training, we get roughly 1.4% top 1 error improvement and 1% top 5 error accuracy improvement. So the accuracy we used here is 89%. It is very sparse based on our previous work. And later I will show this is actually not necessary to have really aggressive sparsity for DSD training. So weight compression and DSD training are having different motivations. One is to make the model small, the other is to make the accuracy higher. So actually, the sparsity shouldn't be the same. No question?
So you said that you can't prove anything about it, but what would be hope to prove it?
Sorry?
What would be even the hope to prove about something like this?
The hope to prove? The theoretical proof, yeah. Yeah, there are a very interesting paper from Princeton that proved the one-layer network, one layer, just the logistic regression, use the iterative of dense-sparse, dense-sparse, dense-sparse can actually improve the accuracy. But my friend actually...
What's the input distribution, what's the assumption?
The assumption, you may read the paper for detail. I'm not expert on that thing. But one layer, they did prove that. Multiple layers, super deep network, they haven't proved that yet. Yeah.
So the moment you go back to dense, you give up all the regularization, right? You give up all the constraints again. So if you then just converge against the optimum of your objective function, you should get the same model. Compared to without doing anything. Right?
So once you are at a local minimum at a very constrained condition, right, and then you suddenly get more degrees of freedom. So the local minimum, there is a paper talking about local minimum are mostly saddle points. And so the more degree of freedom you have, the easier you are to get away from the saddle point and to arrive at a lower local minimum. So by recovering those ways, you are given a more degrees of freedom to get away from the local minimum, probably. And that's why I can arrive at a better local minimum. Yeah.
I think for the training set, it's easy to prove. But how can you prove over the test set? I think for the training set, it's easy.
So the image network, the test set you have to submit online and the restrictions. So we did this is reported as validation accuracy. Although validation accuracy and test accuracy are on ImageNet, previous paper has discussed they are pretty much the same. And for the speech recognition network and the image caption network, all our results are reported with the test set, not the validation set.
No, I mean theoretically. Theoretically, to prove this kind of approach will work for training set, it's relatively easy. But for test set, I don't see any way you can prove it.
That's why we did a lot of experiments.
Technically, you don't want to arrive at a better optimum, right? You want to have less overfitting. So technically, you arrive at a worse optimum that works better in the test set, but it must be worse on the training set, right? Do you observe that? I mean, we look at objective values. Are they getting better or worse?
The training accuracy and the validation accuracy, actually, they are both improving. They both improved, both the training accuracy and the test accuracy, and the loss as well. Yeah. So this is the Google Net result, and this is the VGG-Net result. Originally, we did 2 iterations of dense-sparse-dense training here. And later we found, previously we did 92% sparsity, which means we only have 8% of useful connections. And this resulted in 2.8% and 1.7% improvement of the validation accuracy. But later we experiment with less aggressive pruning, and only with just 1 dense-sparse-dense iteration instead of 2 dense-sparse-dense iterations. We improved the accuracy of VGG-Net by 3.8% in top 1 error and 2.2% in top 5 error. So these are the results on the more recently ResNet 50 and ResNet 152. So the accuracy improvement ranges from 1.8% to about 1% on these networks. And this is the result on SqueezeNet. SqueezeNet has really few number of parameters. So the improvement is best here, roughly 4.3% top 1 accuracy improvement and 3.2% top 5 accuracy improvement. Probably, we guess it's because it has so few parameters that it's really sensitive to you perturb the number of connections and recover from the sparse connections. So next thing we examined is the Baidu research people help us with the deep speech recognition using speech recognition using the deep speech network. This is the architecture. And then we examined two things. So dense training, of course, it improves the accuracy by 0.58 and 1.96% on these data sets, the test set. But how about if we have the same time constraint, right? Training networks takes a lot of time, but if you're iterative, dense, sparse, it takes you a long time, right? People don't want to suffer from the long training time just to get accuracy. Sometimes people does, but what if we have the same amount of training epochs, but comparing with just doing the normal training with 150 epochs versus you do dense for 50 epochs, sparse for 50 epochs, and dense again for another 50 epochs. How do the accuracy compare with each other given the same amount of training time? And we can see that using dense-sparse-dense, the accuracy, the error rate is lower compared with the same number of epochs baseline using the traditional training method.
Equal? I mean, because if you do a sparse epoch versus a dense epoch, do they take the same amount of time? Or?
They take the same amount of time. Sparse one is just applying a mask on the weights. Yes.
You don't have to cut it.
Sorry, so if you look at those numbers, they're very close. With or without using this strategy, the results are very close, right? If you use the same amount of training time.
Yeah, they are
very close.
They are very, not that
different.
different.
To see whether you have the gain because you also need to tune some additional parameters.
What's the question?
So when you decide how you want to switch between dense to sparse and sparse to dense, you have lots of hyperparameters, like how many epochs you want to run for the first dense, the sparse and the dense. Also, what should be the sparsity degree you want to use. So overall time may not be.
Actually, that's not the case. We found that the learning rate, for example, for across all the image recognition networks, roughly decreasing the learning rate by 10 to the minus 2 applies to all the networks for sparse phase. And for the final dense phase, turn it down by another 10 times works across all VGGNet, AlexNet, GoogleNet, ResNet, etc. And for the number of epochs you are required to train, it's actually just observe the learning curve. When it gets plateaued, you just stop. That's simple criteria to observe.
This is because you have been using lots of models on the same task, ImageNet. If you change it to a different task, do you need to spend lots of time tuning those hyperparameters?
No, we didn't. At least for our experiments, we didn't find it really difficult to tune the hyperparameters.
So I do have to challenge your definition of baseline here, because a baseline doesn't seem to be the best you can do with a trivial thing, just letting it run. So I think for this comparison it makes sense, but in the previous results, are these baselines also not the best baselines you can actually get by just letting it train longer, or are those optimized to the best?
Those baselines are what we get from the Cafe Model Zoo. So that's pretty much everyone uses for those networks. AlexNet, VGGNet, ResNet. ResNet is downloaded from Kaiming's GitHub repo. AlexNet, GoogleNet, VGGNet are from the Cafe Model Zoo.
Okay, so we must assume that they did the best they could to optimize those.
Yeah, I assume. Yeah, and finally for the caption generation, we already seen lots of results on the qualitatively and quantitatively. It improved the blue score by roughly 2% to 1.7% to 2.1%. And for example, for this challenging case, this picture, a boy is in a red shirt is climbing a rock wall. It's kind of wrong. Sparse one says a young girl is jumping off a tree. Probably the network mistaken the girl's brown hair with the tree trunk. And the DSD training says a young girl in a pink shirt is swinging on a swing, so it correctly captures the content of the image. And sometimes neither sparse nor the DSD training works. For example, this one fails. A man is sitting on a bench with his arms folded. It's actually not folded arm, but reading a book. And sometimes the sparse one works better than both the baseline and the DSD training version. For example, this one, the sparse version says a car drives through a mud puddle. But the DSD says a car drives through a forest, although the background seems to be a forest. And there are numerous examples. We didn't just pick those examples, but there are many such examples showing. If you're interested, you can send you these pictures. Yeah, the question?
Do you think that this is like possibly doing something like a deep model fusion? Because it's like, you can imagine training 10 different models, and then if you combine them, you get a big gain. And then if you made all of them 90% sparse, you'd have the same number of parameters as your original model and get a 2% gain or whatever over your original model. So do you think that this is doing something similar? Like, do you think that if you did model fusion on top of this, you would see the typical gains that people are seeing by doing model fusion?
By doing model ensemble, it's kind of orthogonal, right?
You think that you would see the same improvements from ensembling?
Ensembling, they are not the same track, right? They are kind of orthogonal methods to improve the accuracy. There is model ensemble, there is data augmentation, and there is such DSD training, and there is like dropout. Dropout is kind of pretty similar, although dropout they have different sparsity at each iteration. They have different sparsity pattern, but DSD pretty much train on the same sparsity pattern throughout the iterations. But I feel this is pretty orthogonal to to model ensemble in the end. Yeah. Your question?
The models where you saw improvements in accuracy via sparsity, did those models also have dropout built in?
Yes, they also have dropout built in. So one section I discussed is that the DSD training is compatible with the dropout technique. Okay, so this figure is the discussion about whether we can do, so previously our work baseline is on the fully trained network from Cafe Model Zoo, for example, AlexNet, GoogleNet, VGGNet, ResNet, for example. Can we, instead of using a fully trained network, right, trained for several days, can we do DSD training on a prematurely trained network, just like the deep speech one we did? So we compared two cases for this kind of premature DSD training. One is the random cut, so randomly prune away parameters, ignoring their absolute value. The other is keep max cut. That is the method we used throughout this work, just based on the absolute value. If the absolute value is small, then we remove them. Otherwise, we keep them. We can see that comparing these two methods, the keep max method improved the accuracy, but the random cut decreased the accuracy. The red line is the original learning curve, similar here. And keep max improved the accuracy, but randomly cut decreased the accuracy. So it really means deep neural network, the sparsity encoded some of the information. Although it seems like you have less number of parameters, then you lose some information. But actually, there are some information inside the sparsity pattern, the connection, which neurons are connected to which neuron have the information. That's why K-max cut is better than the random cut. So this is the first take home for this figure. And the second one is that these green line and the blue line are pruning at different iterations. For the blue one, we pruned after 100K iterations. And for the green one, we pruned after 200K iterations. So pruning at a more mature stage brought better results than just do the pruning at a really, really premature stage. But they seem both better than the baseline if we do no pruning at all. Okay, any questions? Yeah.
You said the original model has dropped out. Does that include ResNet?
That's what?
Does that include ResNet normally doesn't have dropout, right?
ResNet didn't have dropout.
So
I mean, I was mentioning if the original network has dropout, we also use dropout. If that original network doesn't have dropout, we didn't use dropout at all.
That brings another question. Since this DSD stuff is kind of like dropout in some sense, so if you have dropout versus you don't have dropout, does the DSD performance increase?
comparing with dropout versus doesn't have dropout.
No. I mean, maybe dropout contribute the same way as DSD. So if you have dropout in your original model versus you don't have that, maybe if you don't have it, maybe the performance from DSD increase a lot. Do you think so?
So we are pretty, didn't complete, let me see if I get your question. So we are pretty limiting the number of things we want to change. And the only thing got changed is whether we have DSD. The other, we keep it the same. Previously we have dropout, then we still have dropout. Previously don't have dropout, we still don't have dropout. The only difference is that whether we apply DSD training. That's the single variable we changed to examine whether this one will contribute. Does that answer your question? Okay. Okay, maybe.
So what about batch normalization?
Batch normalization is still the same. So for the like ILXNet, VGGNet, previously no batch normalization, we still have no drop batch normalization. For like ResNet, previously they have batch normalization. In this experiment, we also have the batch normalization. Basically, we are using the same proto-TXT. Using
Yes.
with all those stuffs, yes.
So when you do the max cut, I will considering all the layers equal, or are you doing this cut per layer?
Oh yeah, it's per layer. That is per layer.
And so do you see that the connections on different layers have different strength on average?
Yeah, we have seen that one in the first couple of slides, right? There is a blue and green thing across different layers. Conv layers have like 3x you can prune away, FC 10x. Yeah.
Let me just add to this. How about the different matrices in an LSTM? Are you using them, do they have their own threshold, or you put everything together like you plotted it?
Oh, so the LSTM, they have, let me see, that one we have different. Yeah, that's why they have different sparsities, as we can see in the, so we put them as a whole. So so you have IFOG, 4 matrix, input, output. That's when there are eight blocks. Mm-hmm. 8 blocks, we make it a single 1D array and sort it at the same thing as a large. That's why IFOG can get different threshold and sparsities.
Okay, and how about the biases? How do you deal with those?
Biases, let me see. Biases, we pretty much, let me see, put them, I remember for the LSTM, put them in the same plus vector, just add a 1 in the end of the vector and add a 1 column on the matrix. Yeah.
But they're typically bigger, right? So they survive mostly, right? Or what's your...
I didn't plot the pattern for the bias,
okay.
But they are in the same matrix. Oh, that's obviously.
Yeah. There's an interesting paper that I haven't gotten through sufficiently, but it's a kind of a theory paper from Moritz Hart that suggests that if you, for any kind of SGD optimized model, if you converge faster, you tend to generalize better. And I wonder if maybe some of the benefit here is this kind of effect that for most of your weights, they've only been trained for a small number of iterations, and somehow this like confers a benefit for generalization that, because you wipe out, say, 90% of your parameters, and then you start them up, and now these have not seen the data as many times. And this is sort of the source of the generalization benefit. Do you think there's a connection there?
Yeah, from this figure, we definitely see that it converges faster than the original model. It'll be really interesting to see the generalization. For example, apply this to detection tasks and see if the performance is better. I do hope to, yeah, that's a good point, to see if it improves the generalization since converged faster. Yeah, good point. All right, so yeah, let's go to the third part, which is SqueezeNet++. It's a CNN design space exploration. So the problem we are trying to solve here is, you don't have to do the detail, it's just saying there are a huge number of parameters in a neural network. Then how do we tune those little numbers in a deep neural network in an efficient way? So what I proposed is a very small method called sensitive analysis. sensitive analysis. That is for if you are trying to do model compression, which layer do you want to prune more? When you are doing targeting accuracy, which layer should you add more parameters? So sensitive analysis is basically done by across all the layers. This is the squeeze net. Across all the layers, we prune away, say, 50% of the parameters in each layer, and then test the accuracy of the entire model. This is top 5 accuracy. This is the top 5 accuracy. And after pruning, we see how does the pruning affect the total model accuracy. For example, this layer, if we prune away 50% of this layer, the accuracy dropped pretty significantly. Similar with this layer. But for example, this layer, after we prune away the parameters, it pretty much didn't get any hurt of the accuracy. So it meaning, as a very simple heuristic for me to, if I want to add parameters, I will add parameters to this layer and to this layer. If I want to prune parameters, I don't want to prune these layers too much, but those layers. And I have also seen those really sensitive layers are all 1x1 convolution kernels. And 3x3 convolutions are typically less sensitive than 1x1 convolutions. And this too dense usually happens very close to the pooling layer in this example. So this is the result. When I add some parameters to this layer and this layer, the model size got increased, but the accuracy improved as well. So the next thing is one of our ICR poster. It's a really small work trying to use even-sized kernel. These are all design space exploration. So previously, people all use 3x3 kernel, 5x5, 1x1. So we asked the question, can we use 2x2 kernel? And we only experimented on the small network, MNIST and CIFAR. And this is result on CIFAR. So this is the baseline model. We have 8.54 error rate. And this is number of computation. And if we use 2x2 kernel, it reduced the computation by roughly by half, 9 divided by 4. But the accuracy pretty much similar. But if we increase the number of, having the same number of computations by increasing the number of channels using 2x2 kernel, we can see that the accuracy actually improved, the error rate got dropped. So 2x2 kernel is kind of more hardware friendly because if you have 4x4 kernel, that is 16. 2x2 kernel is 4. That's exactly 4 processing engines. So that's why we did this experiment to future hardware engineers want to explore with even number of kernels. This give a little intuition it might work, but more experiment need to be done on the large ImageNet data set. So this is the third piece of work of design space exploration, of macro texture design space exploration. So it's enlightened by the Microsoft research work on the ResNet, adding the bypass layers. So we add the similar thing to the squeeze net, and we tried simple bypass layer where those have the same number of channels, and complex bypass where the number of channels are different. We use 1x1 kernels to decouple the difference in the number of channels. So this is a figure illustration. We saw very strangely that the simple bypass actually worked better than this complex bypass. So improved the accuracy by roughly 3%, rather than the complex bypass only improved the accuracy by 1.3%. Okay. So all this concludes the software part of my work. Now we can finally go into the hardware part, as many audiences asked about the efficiency of sparsity and also the lookup, the one level of indirection. Let's see how is that can be solved with building specialized hardware. So the motivation is that, again, I bring this figure again. Memory reference is really expensive. This is in log scale. Memory reference is 2 or 3 orders of magnitude more energy hungry than multiplication and add. So we really want to decrease the number of memory references. So having smaller model will be able to allow us to put all the weights on SRAM cache instead of going to off-chip DRAM. So deep compression, previously proposed deep compression solved the model size problem. Model is smaller, but it creates another problem, right? It has irregular computation pattern, right? We have sparsity, we have a level of indirection, we have to look up the code book, we have relative weight instead of absolute weight. So CPU or GPU are pretty good at dense linear algebra. So we created efficient inference engine, which is a sparse matrix, sparse vector, because after ReLU, the vector is also sparse. We also take advantage of the sparsity in the activation after the ReLU function. And it's indirectly indexed because we want to save the space. So we don't encode the index with 32-bit, but using only 4-bit to encode the index, which location each sparse weight is at. And weight shared matrix vector accelerator. So this is a matrix vector accelerator. It's a basic building block of proof of concept. It doesn't support convolution yet, but I will talk about how to use this as a building block to support convolution in the end. So this is a paper we accepted by ISCA happening 2 weeks later.
Is V ever going to be sparse in any of your scenarios?
Sorry?
Is V ever going to be sparse in any of your scenarios?
The V, for example, in image recognition, we use ReLU, then V is sparse. But for speech, people use TitanX, that may not be sparse. Yeah, we experiment with both in our benchmark. So again, this is the layout of the chip. We did everything before tape out, did synthesis, place, and route. And then it's a sparse indirect index with shared matrix vector accelerator. So let's see its features. First, it takes advantage of the sparse matrix. There are 10% sparsity in the matrix, as we discussed before, which saves 10 times the computation because we can completely don't do computation on the 0 weights and saves 5 times memory print. Why 5 times instead of 10 times? Because we also need to store the index of the weights in the sparse format. And this has been taken into account in all previous numbers. And we take advantage of the sparse vector as well. So we profiled AlexNet, VGGNet, GoogleNet, and found that after compression, roughly there are 3 times sparsity, sometimes even more. For VGGNet, I remember the last column layer is roughly 5x sparse for the activation. It's really sparse. So on average, it is 3x activation sparsity after the ReLU function. So finally, we have the weight sharing. So each weight is encoded into 4 bits, really few number of bits, which saves 8 times compared with 32-bit floating point number. So all these features make it possible to fit all the weights on the SRAM instead of going to the DRAM, which, as shown in the previous figure, it takes 120 times less energy to stay on chip than you have to go to off chip. So we distributed the storage and processing across a 2D array of PEs, and then use this tree structure to broadcast the activations to all the PEs. So each color shows one PE's allocated weights. So this is a matrix, and we divide it by, say, for example, we have only 4 PEs, then each PE is responsible for a single row here. And the good thing for this is that it only do the local reduction. It doesn't have to be global communication to reduce the weights. But we do need global communication through this tree distribution network to broadcast the non-zero element. For example, we have a non-zero detector circuit that output one non-zero element at one cycle. For example, first one, we have A2 here. The first 2 is 0. And we broadcast this A2 to all the PEs. And then it's multiplied by the non-zero elements here. So remember, in the memory, these zeros are not stored, but only those non-zero elements are stored in the SRAM. Oh, yeah.
You have to deal with the issue of skew in your matrix.
skew.
So like you have some rows that have a larger number of non-zeros, so you have imbalance on computation.
Yes, that's a good question. We have a buffer to decouple the imbalances between the different PEs. For example, PE1 have 100 tasks. PE2 have 200 tasks in one column. Then that one will finish faster. But we allow a FIFO buffer to decouple this kind of balance. Overall, the matrix is balanced, but there are local imbalances. And we swept the number of stages we need, the depth we needed in the FIFO buffer. We have results later.
If I don't have sparse vectors, do I end up having to just broadcast the whole dense vector to every PE? Because you don't know ahead of time what non-zero values you actually need until you get there, right?
Yes, we have after the whole activation is there, we have the leading non-zero detector to detect which element is non-zero. And it takes multiple cycles for all the PEs to consume this non-zero element. For example, PE3 this is one cycle, this is another cycle, 2 cycles in this case, but there are way longer in the real matrix to consume this element. During the time they are being consumed, this circuit can find the next non-zero element. Does it make sense?
So the zero detector is just for zeros in the vector. So assuming there's no zeros in the vector, you still have to send like A2 to everybody. It has to go to all of the PEs, and then you might have bubbles in your pipeline because you just have to discard it, but it takes up bus cycles.
So this non-zero elements, you have to broadcast. You do want to broadcast it to all the PEs, but you don't want to broadcast this one to all the PEs.
But
yeah.
I'm just saying in the case where you don't have a very sparse vector, like say my vectors are generally dense, like I don't have
this vector is generally dense.
Yeah,
it's okay.
Right, then I have to broadcast it to everybody.
That is okay. For example, A4 and A5, you broadcast A4 to all the PEs to process them, and after they are done, you broadcast A5 to all of them. That is totally fine. Yeah. So this is the special logic we inserted into the circuit. So we have 4-bit virtual weight. We do a weight lookup to get the 16-bit real weight. And for the index, we store the relative index in the CSC format to save the space, and do an index accumulation to get the 16-bit, the absolute index to feed to the memory. So a little bit about evaluation. This is pretty much a lot of word, but it's the pretty standard ASIC design flow. We first designed accurate C++ cycle accurate simulator as a design space exploration and for verification. Next step, we did the Verilog in RTL, verify the output with the golden model. And thirdly, we did the synthesize with the Synopsys design compiler under TSMC 45 nanometer. This is kind of old, but that's what our school currently have. And then we did the place and route with the IC compiler and used Kaiktai to estimate the SRAM power. Finally, we annotated the toggle rate from the RTL simulation because the power is equal to CV squared times the frequency. We need to get this frequency, the effective frequency to estimate the power consumption. That's why we used the primetime PX tool to annotate each circuit node's switch factor annotated to the actual node. So this is the layout of the chip. This is the result of the power and area across different building blocks. For example, memory takes pretty much all the area. For example, this is the sparse matrix, and these are the metadata we have to store those pointers in the CSC format. And this is the actual arithmetic unit, which is pretty small compared with the SRAM. So all the weights are storing here and here. So the benchmarks we used here are the FC layers of AlexNet, VGGNet, and NeuroTalk. Remember NeuroTalk, since the activation function is not ReLU, the activation sparsity is 100% for NeuroTalk. And for AlexNet and VGGNet, the sparsity of the activation is roughly 1/3. And the weight activation ranges from VGG at 4% to some of the layers which is 25%. Yeah. And the number of flops, we can see here that the number of flops required is the number of weights here times the previous layer's activation sparsity. So it's only 3%, 10%, even 1% to 11%. So the actual computation, the actual number of multiplications and adds done on this hardware is a lot smaller than the dense accelerator. So that brings another question. So during the paper rebuttal, people complained why you have less flops, the number of floating point operations per second you can do. Because the effective, we are considering the application throughput, not the arithmetic throughput. Doing one arithmetic here, for example here, typical number is 3%. The original dense hardware, you have to do it 100%, but here you have to only to do 3% of the original work to achieve the same accuracy. So remember, we have seen this before. Now we have a last bar, which is done by EIE across all these benchmarks. So this is about the speed up, and this is about the energy efficiency. We may just look at this geometric mean about the CPU, GPU, mobile GPU, and efficient inference engine, which is 180 times faster compared with the CPU without compression. And it's roughly 13 times faster compared to a GPU without the sparsification, and still faster, like 4 times faster than a GPU that used the sparsity. And this shows the energy efficiency in the log scale. If we see the geometric mean, EIE is 24,000 times more energy efficient than the CPU without sparsity, and roughly 3,000 times compared to this one, 3,000 times more energy efficient than the GPU without the optimization. So we may wonder, where does the 3,000 times energy saving come from? So it's summarized here. There are 3 factors, mostly because you don't have to go to off-chip. So first one is the matrix is compressed by 35 times. I compare with, so you have less work to do, right? You have less computation to do. It's like you have less bricks to carry for a Super Mario. And then you don't have to access DRAM anymore to fetch the weights. Everything is locally on SRAM, on-chip SRAM. So there's no need to go off-chip, which gives you another 120 times energy saving per access. This is you have less access. This is you have 100 times less energy per access. It's like you can carry bricks from Stanford to Berkeley, and now you can just carry from Stanford to Palo Alto. It's a lot more closer. Finally, we take advantage of the sparse activation, which saves the 3 times, although some speech recognition doesn't have this factor. It's like you have lighter bricks to carry. Question?
Go back to the numbers. So you mentioned that the CPU GPUs only are using pruning in this example.
Yes.
So why doesn't quantization and weight sharing help you there too? Because you can keep everything on-chip cache at that point.
Yeah. So we are using the, I believe with more engineering, you can definitely do that. But the existing library, for example, cool-sparse and the MKL doesn't provide that interface. I believe more engineering work can. Yeah.
CPU, GPU,
Yes.
if you exploit the other 2 techniques.
Because
in your EIE, you're using all of the techniques, right?
Yes, if you are diligent and delve into the MKL libraries and cuBLAS libraries, there's room. Yeah. And these are some, this is the question we just mentioned about the imbalancing between the PEs. So different PEs may have different workload. Some of them may get more, some of them may get less. That's why we created the FIFO to decouple the idleness. And we can see if with an increasing number of FIFO depth, 1, 2, 4, 8, 16, pretty much at 8 or 16, the utilization, which is the number of useful cycles divided by the total number of cycles, is roughly 90%. Finally, we use the FIFO depth of 8. And this shows the scalability of different number of PEs. Remember, we have different PE structure, depending on the model size. If we have more, for example, this model is so small that it doesn't make sense to increase the number of PEs to that much. But for the other large matrices, it's pretty scalable. This is roughly on average 220 with 256 PEs. So the scalability is pretty good. If you want it to be faster and tolerate more power, you can use more number of PEs. And this is some hardware design space exploration of the total SRAM width you want to use. So the wider the SRAM width, the more energy consumption per axis, but you may need less number of axes. Due to the balancing issue, multiplying them together gives the optimal SRAM width roughly 64 bits to 124 bits here. I believe what we used is 124 bits. So this is the arithmetic precision after the weight sharing. So remember, weight sharing, that is the mixed precision. We store the index with 4 bits, but the real code book, we still have to store them in how many bits? Let's see. With 32-bit, it's pretty accurate. All the way to 16-bit integer, it's still pretty accurate. But once the code book also go to 8-bit, it begins to drop the accuracy significantly, although the energy is also lower here compared to here. So the optimal working point with low energy and high accuracy, we used 16-bit integer for the code book. So this is a comparison with other platforms of CPU, GPU, mobile GPU, FPGA, and this is ASIC. This is also an ASIC, and this is our EIE with 64 PEs and with 256 PEs. And our previous work are using 28 nanometers or even better, but our school only have 45 nanometer technology. That's why we projected to 28 nanometer technology. So this is the real simulation result, and this is projected result. So some of the useful columns to look at are, for example, the memory type. All previous things are, except this one. This is spiking neural network. They are using SRAM. All previous are using DRAM or EDRAM, and we are using SRAM to store the weights. And quantization strategy, previous work are using 16-bit or 12 or 32-bit. But True North is a spiking neural network, so it's just 1 bit, and ours is using 4-bit. And so this is the area. We are pretty small compared with all previous networks, and we hold the maximum deep neural network size compared with our previous network. We can do much larger networks, given even smaller area. And this is the power consumption. CPU is roughly 70 watts, GPU 150 watts, mobile GPU 5 watts, FPGA 9 watts, 大电脑 is 16 watts. And True North is really energy efficient. It's only 0.18 watts, and we are 0.6 watts or 2 watts compared with using different technology and different number of PEs. So the throughput for matrix and vector multiplication, we are pretty better than the True North and better than the FPGA. And with 256 PEs, we can have better throughput than the ASIC work and better area efficiency as well, and better energy efficiency as well, mostly because we are having the compression together with the efficient hardware design. It's a software and hardware co-design work rather than the previous work mostly on the hardware side. Yeah, we have seen this before. So some readings if you are interested. Tech Emergence, Hacker News. Okay, so in conclusion, we presented the efficient inference engine optimized to work on the compressed network, which is a hardware-software co-design work. So by leveraging the sparsity in both the activations and the weights, EIE can reduce the energy needed to compute the TP2 FC layer by 3,000 times. So with wrapper logic of EIE, 1-by-1 convolution and 3-by-3 convolution is possible, but EIE is just a building block. So a little bit of recap of all the 4 topics I mentioned today. So first, we talk about the model size, how to compress the model, make it smaller, have the same accuracy by sparsity, taking advantage of sparsity, and take advantage of the trained quantization. And secondly, we talk about the regularization. Given the same model size, how do we improve the accuracy? And we discussed the training DSD, Dense-Sparse-Dense training, which is our pretty recent work to reduce overfitting by the dense phase, sparse phase, and recover all the weights back by the dense phase. And then we discussed the CN architecture design space exploration. How do we size different layers? How do we do sensitive analysis to decide which to prune and which to add more parameters? And we also discussed the even kernel may help. Will help with accuracy and hardware friendly make it. And finally, we discussed about the EIE, which is efficient Inference Engine, software hardware co-design, works directly on the compressed deep neural network to improve both the speed and the accuracy and the energy efficiency. And thanks to my collaborators with Stanford, NVIDIA, Tsinghua University, and Berkeley. And that's all. Thank you.
Thank you very much. I learned a lot, very inspiring. So we have 7 minutes for questions.
Alexei?
So the results look very impressive for the fully connected layers. Do you expect the same progress for the fully convolutional layers? Like if you take a resonant, right, most of the time you spend there's just a single relatively small fully connected layer.
Yeah, maybe after 6 months, I can answer this question better since we are still working on that part. Yeah. Yeah, question?
I forget if you showed this, but can you redensify after dense-sparse-dense and not lose anything?
Yes, you can do dense-sparse-dense iteratively.
And then you basically end up with, but after, can you sparsify it at the end and not lose anything at the end?
Oh yeah, that's for if you want to both increase the accuracy and then decrease the number of size. I can show you the intermediate result of doing 2 iterations. For example, in the this is VGG 16. So this is dense, and then sparse, and then dense, and then sparse, and then dense. So if you are here, you get like 60% sparsity, but you have higher accuracy.
And have you ever tried to do it at the end? So that can you? I mean, like, assumedly, if you do like 7 iterations, you'll stop getting improvement. Like, can you always, like, eventually, will the dense one always be better than the sparse one?
I didn't try that much, but I just tried 2 iterations.
Okay.
Maybe that's worth trying. Yeah, more iterations. Yeah.
I had a question on the EIE. For the code books, are those stored centrally or is it replicated? I'm just curious.
Let me put out the.
You're not using that. Oh, okay.
Right. There's no Huffman encoding in the EIE, right?
No.
Or is there?
No, there's no Huffman encoding and decoding in EIE.
But there is a code book, right?
There's a code book that comes from the weight sharing.
That comes from the quantization.
Yeah,
The quantization.
just storing the centroid values.
Yeah, that's only 16, actually only 16 numbers, and it's replicated across all the PEs.
Oh, okay. So it's so small, you don't.
It's very small, 200 and just pretty few, 16 numbers, yeah.
That's enough to support all of the networks that you care about.
Yes.
In the CPU, can you go to the speed graphs that you had? In the CPU numbers, what matrix multiplier are you using? Like the CPU compressed, the blue one.
This is using the MKL, which I found is better than Atlas.
Okay. Are you using MKL for all of for the dense one as well, or?
Yes, MKL for the dense one, MKL for the sparse one,
Okay.
and cuSparse for the dense one, cuSparse for the sparse one. Similar for the mobile GPU. Yeah.
For the EIE layout, what sort of capacity did you need to store of metadata on chip? Can you talk a little bit more about the metadata?
Yeah,
What
the
exactly
metadata is the
storing?
pointer instead of the weight. If you look at the CSC format, you need to know, yes,
Okay.
they are stored consecutively. Where are the weights? That's the point.
And how much
We can see here.
allocating?
So this is pointer read, and the area is this is the overhead. This is the metadata compared with the usable data. It's roughly 20%.
Okay, so actually I have a question.
Yeah.
So you compared your design with an FPGA, but you said they really focused on the hardware only. So what would you expect if you did all the things you did with quantization and so on, and would redo basically the work on an FPGA?
I think that's promising thing to do. Although maybe you have the constraint about the on-chip DRAM resources you might have. Is it enough to store all the weights on chip? But for ASIC, you pretty much have the freedom to choose how large your SRAM are. So it's really critical to make it compressed and fit the specific FPGA resource. Otherwise, you may have to buy a larger FPGA to fit them on the board. Yeah.
How much on-chip do you instantiate?
So this on-chip memory we have is roughly 8 megabytes. Yeah.
Okay, any more questions? So let me just say one thing. I'm very impressed by your speed up slide. If you have to report your speed up on a logarithmic axis, you're really on a good place.
Okay.
Okay, so I would like to thank the speaker one more time.
Thank you.